Okay, so hello and welcome everyone to the fifth lecture of our CUDA program. So in the previous lecture, we saw we saw how the threads are organized on the GPU, and we also saw how a grid is associated with a kernel launch, and then we saw that grid is composed of thread blocks, and so multiple thread blocks forms a grid, and and then we saw that there are multiple dimensions associated with this grid and thread blocks, and so we saw that there can be at most 3 dimensions associated with this grid and thread blocks, and then we saw something called as thread ID and block ID to access the grid as well as thread block in these 3 dimensions. And then we saw the particular examples associated with 2D. Then we saw the particular examples associated with 2D grid and 2D thread blocks, and 1D grid and 1D thread blocks. And there we stopped in the last lecture. And for the today's lecture, we are going to see how we can launch the kernel for the how can we launch the kernel for the large amount of data when the data size is huge. How can we launch the kernel? Then we'll see the GPU computation hierarchy. We'll see what is the warp, and then at the end probably we'll see what are some of the issues such as thread divergence and such issues we'll see. So that's the brief outline for the today's lecture. So with this, let's get started. Okay, let us see how can we launch the kernel for the huge data size when the data size is huge, and how can we launch the kernel. Let us understand it by this example. For example, let us say that we have a vector or array of very large size, and we want to launch the kernel in such a way that we have one thread for each element of that array. So one thread will do computation on that particular element of the array. We want such type of we want to launch the kernel in a such a way that we can have one thread for each element in the array, and we want to initialize that array. So for that, let us see this example code. So here initially I'm including the stdio.h and CUDA.h, which is normal for any CUDA program that we do, and then I'm defining the block size as 1024. Then coming to the main this time takes 2 command line arguments, which are argc and argv. Argc and argv. So the first command line argument is named as nn, so it denotes the number of command line argument that the user will pass during the runtime, and the second argument is named as str, which will store the each and every command line argument passed by the user during the execution of ./a.out. So what we'll do is we'll take the first command line argument passed by the user. Here we'll assume that the first command line argument passed by the user denotes the number of threads with which the user wants to launch the kernel. So it actually it's both the number of threads with which the user want to launch the kernel as well as the vector size of the vector that he wants or she wants. So as we want one thread for each and every elements of the array, uh, so and denotes both size of the array as well as the number of threads with which we want to launch the kernel. So uh, yeah so first argument is a string which stores the integer. So first of all, we need to convert this string to an integer using this built-in a2i function given in C library. So we convert that string, which is the first command line argument, to an integer and store it inside this variable n, which is an unsigned integer variable. Then we declare two pointers, unsigned integer pointers, which is star vector and star h vector. So h here stands for host, as we saw in our previous lecture, and vector will store the address of some memory location on GPU. So okay, so as we saw in previous lecture, we'll allocate the memory on GPU using CUDA malloc, and using CUDA malloc we'll allocate the memory on GPU of size n unsigned integers, and then the starting address of this allocated memory location will be stored inside this pointer vector, which is declared here. Then after that we'll again declare the memory of size and allocate the memory of size and unsigned integers on the CPU using malloc, and the address to it will be stored, and the starting address of this allocated memory will be stored inside the H vector. Once we are done with this, we will now uh, calculate the number of blocks with which we want to launch the kernel. As I mentioned in the previous lecture, the block size cannot exceed, a block cannot have more than 1024 threads, and it might happen that our user specify the uh, integer value with which he or she wants to launch the kernel to be 1 million. So in that case, we just can't launch the kernel using 1 comma 1 million, because the number of thread here we can't launch the kernel with 1 comma 1 million, because number of threads in a particular block are restricted to 1024. We can't launch one block. We can't launch a kernel with a block having more than 1024 threads. So in that case, we need to calculate how many thread blocks we will need, considering that the thread blocks, each thread block can only have 1024 threads. So considering this n as a very large number, which is specified by the user, will calculate what is the size of what is the number of blocks that we want to allocate, which can be calculated by n divided by block size. Block size is 1024. So n divided by block size will give us the number of blocks with which we want to launch the kernel. So please note here the C function. So if the n is not perfectly divisible by the block size, then we'll launch one more block to just compensate for the extra elements in that array. And yeah, then once that is calculated, we will print that number of blocks which are calculated here in this printf, and then we'll launch the kernel with n blocks, which is number of blocks that we calculated here, and the block size, which is 1024. And then we'll pass this vector. Vector is the array that we declared here. The array which was allocated memory on GPU. Its address was stored inside this pointer vector. So we are passing that address here to the kernel. And once the computation of kernel is finished, we copy the data back from GPU to CPU, that is from vector to H vector, using CUDA memcopy device to host, and we are copying n elements back from GPU to CPU, and then we are printing all those n elements. Yeah, and inside the kernel, what we are doing is we are first computing the ID, as we saw in the previous lecture. Here we are computing the ID with the same equation that we saw in the previous lecture. And what we are doing is we are initializing each element of the array with the ID of that thread. So thread with ID 0 will initialize that element, will initialize the zeroth element with the zeroth element in the array with 0. So the thread with ID 1 will initialize the first memory location in array to 1, and so on till the last thread. And yeah, so that is how this code is organized. So moving on, there are two issues with this code, and let us look at let us look at this both issues one by one. So first issue is that uh, the first issue is about this at this line here in the calculation of n blocks. So let us see what is the issue. Let us try to understand this issue with an example. Let us say that I have 10. Let us say that user have specified n as 1025 instead of any number which is divisible by 1024. Let us pick that number as 1025. So user specified n as 1025. Now, so this n is 1025, which is an integer, and block size is also 1024, which is an integer. So way this integer division works in C is that when we'll divide 1025 by 1024 in C, it will give 1. It will not give 1 point something, because it's an integer division, and that seal of 1, which is and this seal of 1 will be 1. So seal of 1 will be 1, and hence we'll be launching the kernel. So n block will be 1, and so we'll be launching kernel with 1 comma 1024. and hence we'll be launching the kernel with just 1024 threads. However, user specified that he or she wants to launch the kernel with 1025 threads. So that is the first wrong thing that we are doing. Instead of launching the kernel with 1025 or more threads, we are launching it with less threads. We're just launching it with 1024 threads instead of 1025. So that's the first issue, and that is caused due to this integer division here. So that's the first issue with this code. The second issue is here. So let us understand the second issue again by example. So yeah, so let us say that we fixed that issue. First issue we fixed, and user specified n as 1025, and yeah, we did the floating point division here. So 1025 by 1024 will be 1 point something, and seal of that 1 point something will again be so that seal of 1 point something will be 2, and the n blocks will store the value 2, and the kernel will be launched with 2 comma 1024. So kernel is launched with 2048 threads, but now since kernel is launched with 2048 threads and the vector is only declared of size 1025, so here vector declared on GPU is only of size 1025. So here what the issue will occur is that we'll be accessing some of the threads, in fact many threads which have ID from 1025 to 2047 will be accessing the invalid memory location here. So that is the second issue, that many threads will be accessing invalid memory location if the number of threads launched are more than the size of the vector that we declare on GPU. So in order to avoid both this issue, what we can do is, okay, so first of all, as I mentioned, we need so to avoid so okay, so first of all, as I mentioned, the first issue is that we need floating point division here, and second issue is that access can be out of bound at this line. So in order to get rid of both these issues, what we'll do is, first of all, we'll convert this integer division to floating point division by either typecasting n to float or block size to float. Here I have typecasted n to float, and uh, to to solve the second issue, what we'll do is we'll add a guarding if condition here, that if id is less than vector size, then only we'll do vector of id equals to id. So vector size is the size of the array declared on the chip. So vector size is passed here, if you see, as n, and n is what the user specified. So if user specified 1025, then vector size will be 1025, and all the threads having id more than 1025 or more will not execute this statement. So by putting this guarding if condition, we are safe. I mean, we won't face any sec fault or any such issues on GPU after putting this guarding if condition. And by this adding these two things, we can solve both the issues that we saw earlier. And yeah, so moving on to the next slide. So next thing that we are going to see is a simple matrix squaring application. So first of all, we'll be looking at first of all, we'll be looking at its CPU version. So this is a simple CPU matrix squaring application. Uh, so here we are multiplying two same matrix, and this code looks very similar to the matrix multiplication code. So here, as in the matrix multiplication code, we have this triply nested loop, each going from 0 to matrix size. Yeah, and as we have in the matrix multiplication code, for each entry ij, we are doing we are first calculating ik into kj. So we are multiplying that two things and then adding the result into uh, the result matrix at the location ij. So one thing that you should note here is that even though we are doing matrix operation, I mean we are doing matrix operation, which is some two-dimensional data structure. Still, we have declared the matrix as one-dimensional array. So in order to access that one-dimensional array in two-dimensional form, we are using this thing, ii into matrix size plus jj, and similarly here ii into matrix size plus kk, and kk into matrix size plus jj. So that is how we can access a one-dimensional array in way the two-dimensional matrices are accessed. So yeah, that is one point that I want to highlight. And yeah, this is a simple matrix squaring code that is highlighted here. And when we run this code on CPU, the time taken to run this code for the matrix of size 64, which is 64 cross 64 matrix, is 1.5 to 7 milliseconds. So that is the time taken for matrix of size 64 cross 64. And yeah, so that is okay. This is the time taken for the matrix squaring on CPU. But let's say we want to parallelize this code on the GPU. So how can we go about parallelizing it on GPU? So one of the simple way can be one of the simple way is to just parallelize this first outermost for loop, and that is what we'll be going to see in our next slide. So in order to parallelize the outermost loop, what we'll do is we'll launch kernel. We'll launch kernel with 1 comma n threads for n is 64. Please note that n is 64, and we'll be passing matrix and result, which are again two matrices. Uh, so yeah, that those are the two matrices that we'll be passing to the kernel, as well as this n, which is the size of the matrix, which is 64. Now, once these things are passed and the kernel is launched with n threads, which is 64 threads, uh, in order to parallelize that outermost for loop, what we will do is we'll declare, we will calculate the ID. So this ID value is calculated using the same equation as we saw in the previous lecture here. And yeah, so once that ID is computed, we'll see that so threads will have their ID going from 0 to 63. Since there are 64 threads, IDs will go from 0 to 63, and each thread will be each thread will be executing one loop. Each thread will be executing the one loop of the one iteration of the outer loop. So please note, in that previous slide, I was going from 0 to matrix size, and matrix size is n. Matrix size is again n only, because n here we are passing, which is again stored in matrix size. So matrix size is n, and this code is written in such a way that one thread will execute the one iteration of this loop, of this outer loop. So outer loop is removed, and one iteration will be taken care of by one thread, and the entire loop is now gone. And yeah, so rest of the code remains same, except that wherever there was I, now we need to replace that by ID. So if you remember, here in the previous code there was I here and I here two places. Now that is replaced by ID. So yeah, that are the two minor changes that we want to make. Rest things are the same. So we have these two nested loops. uh, yeah so rest of things are same. And so that two nested loop remains the same. Now if we time this code if we time this GPU code using some clock function or get time of the day function, then we'll see that this code takes even more time to execute than the CPU code. If you see this, CPU code takes 1.52 milliseconds, while GPU code takes 6.39 milliseconds. So we need to understand why does this happen. So there are two reasons here. First of all, the first reason is that we are doing a lot of work serially. If you see, there are two. We have just parallelized one of the loop, but still these two loops are there here, and this is a lot of work still done by a thread in sequential manner. And if you remember, each core of GPU is much weaker than the core of CPU. So even though in CPU we are doing n cube amount of work, and on GPU we are just doing for this code we are just doing n square amount of work for each thread, still the CPU code will beat the GPU code, because there is still a lot of sequential work that is being done for each thread. So that is one. So first point is that a lot of sequentiality is involved. The second point is we are not exploiting the GPU at its maximum extent, because we are just parallelizing the outer loop, and the outer loop was of size 64, right? It was running from 0 to 63. So the maximum amount of parallelism that we can achieve by parallelizing in this way is just 64, right? Because each thread is taking care of one iteration, and there are just 64 iterations. So the maximum amount of parallelism that we can achieve is 64 for this version of code. And as I mentioned in the first lecture, that the number of cores on GPU are much larger. The number of cores on GPU are in thousands, while here we are just exploiting 64 here. So we are underutilizing the GPU. That's the second issue. First issue is there is a lot of sequentiality. Second issue is we are underutilizing the GPU cores, and hence the performance is poor compared to CPU. So in order to improve this version even further, what we can do is we can even parallelize the second loop here, inner loop here, which consists of J, uh, which consists of looping variable as J. So yeah, so let us try parallelizing this J loop. So how can we do this? So okay, so instead of launching the kernel with 1 comma n thread as we did in our previous example here, what we'll do is we'll now launch the kernel with n comma n thread, which is where n is 64. So we are launching kernel with 64 into 64 threads, and again we are passing matrix and result as we did before. Okay, so yeah, and matrix and result we are passing, and n again we are passing, which is stored in matrix size. And now we are inside this kernel, and the kernel receives this arguments from the main function, these three arguments. And yeah, we compute the id as we did in our previous lecture using this formula. And now this id will go from 0 to 64 into 64, which is from 0 to 2047. Sorry, 64 into 64 minus 1 it will go. So it will go from 0 to 2047 because we are launching kernel with 64 into 64 threads. So id will go from 0 to 2047. And in order to get unique tuple of ij, what we'll do is we'll use this trick or this formula. So we'll calculate ii as id divided by matrix size and j as id mod matrix size. So let us see how this works. For thread number 0, id will be 0. So 0 divided by matrix size will be 0, and 0 mod matrix size will be 0. So ii and jj will be 0, 0. For first thread, again it will be 1 divided by matrix size, which is 1, which is 0, and 1 mod matrix size, which is 1. So 0 comma 1 will get, which is again a unique tuple. For the second thread, again 0 will get for I, and for j will get 2. And this will continue for up till the n minus 1th thread. For n minus 1th thread, id by matrix size, which is n, so n minus 1 divided by n will be 0, and j will be n minus 1 mod n, which is n minus 1. But for nth thread, id divided by matrix size, which is n by n, is 1, and j is n mod n, which is 0. So for nth thread, we'll get 1 comma 0, and for n plus 1th thread, it will be again n plus 1 divided by n, which is 1, and n plus 1 mod n, which is 1. So 1 1 will get, then it will continue so on for other threads. So the thing here to observe is that by using this two formulas, we'll get unique pair for I and j. So unique tuple will get for this unique tuple for ij will get, and yeah. So after doing that, once we have this unique tuple for ij, what we can do simply is we can simply copy paste the code that we were having in the previous version for k here. Yeah, so not for this, so not this one, but this one for k, that we whatever code that we were having here, we can simply put it over here, uh, and yeah, so that's it. Rest all things are same, and yeah. So the k loop is not parallelized here. So I and j loop are parallelized, and yeah, so rest of the computation is same as we do in the matrix multiplication or matrix squaring. And one thing to observe here is that we have improved the amount of parallelism here. So initially the amount of parallelism was restricted to 64 because we are just parallelizing the outer loop. But now the amount of parallelism is much higher, which is 64 into 64, since we are launching kernel with n comma n threads. So amount of parallelism here is much higher, which is 64 into 64 for this code. So we have solved the second problem that I mentioned earlier, and we have also solved the first problem. That the first problem was amount of sequentiality is very high. So here we have also solved that problem because now the sequential portion is just restricted to this k loop. So yeah, so amount of sequentiality is also reduced, and parallelism also improved. So if you time this code, which is the version 2 of the matrix querying, then you will see the time taken for this code to execute is 0.1 millisecond, which is lesser than the version 1 that we saw, what the time taken by the version 1, which was 6.39 milliseconds, and it is even better, and it is also better than the CPU time, the CPU matrix querying code, which was 1.52 milliseconds. So yeah, so by parallelizing both the loops, we were able to achieve good performance benefits for this matrix querying application on the GPU. Uh, and yeah, so one more question is that can we parallelize the K loop? So parallelizing the K loop won't be possible, because when we parallelize the K loop, what will happen is that for each entry in this each cell or each entry in this matrix ij, which denotes an unique entry in that matrix, uh, there will be multiple threads which will be adding to that same element in that matrix. So there is something called as data race that will happen. So parallelizing the K loop won't be possible, because due to data race there might be some correctness issues. So we should be careful about it, and hence the parallelizing the K loop is not possible unless we do some synchronization here. And yeah, so for now we'll leave here, because synchronization part we haven't covered. But yeah, please remember that there is something called as data race when we try to parallelize this K loop. Yeah, so that's it for this matrix querying. And one small homework that I want to uh, give to you people is that try exchanging this I and j variables and see if the results that you obtain for this matrix querying are correct. Let's say if the results are correct, then you should try to observe what is the change in the timing that you observe, like whether it is more than this zero point 0.1 milliseconds or less than this, and how is it compared to the CPU time and GPU version 1 time. So that's a small homework that I'll leave for you to do. So moving on to next slide. Now we'll see this GPU computation hierarchy. So at the lowest level on the GPU, we have something called as thread. And yeah, so the thread is the smallest individual unit, and or it is something like a worker, which is like a single worker on the GPU. And this this such 32 such threads together form something called as warp. And the important point to note about this warp is each and every thread inside this warp executes in SIMT fashion, which is single instruction multiple data. So let's say there is an instruction I1, and then there is an instruction I2. Then all the threads of the warp will first finish the instruction I2, and then only they instruction I1, and then only they'll move to the instruction I2. So it will never happen that a particular thread of a warp is executing the instruction I1, and the other thread of a warp is executing the instruction I2. Yeah, so I repeat that it will never happen that a particular thread of a warp is executing the instruction I1, and another thread of that same warp is executing the instruction I2. Uh, yeah, so that is one thing that is called a SIMT execution. And the uh, and multiple such warps together forms a thread block. Multiple such warps together forms a thread block. And yeah, as we saw, the thread block can have at max 1024 threads. So at max there can be 1024 by 32, which is 32 warps inside a block. So at max inside a block there can be 32 warps. And yeah, each of this warp executes in same fashion. And one more thing about this block is that for for threads for all these threads inside a particular block, there is something called as fast synchronization that is available. So we'll study that in synchronization lecture, that there is something called as sync threads available for these threads within a block. So how this sync thread works is like it is something like a barrier. So so like all the threads within that thread block will synchronize at that point where that sync thread function is written. So what will happen is that one thread is waiting for some instruction to finish, and let's say other thread has reached that sync thread function, So that at that point that thread will wait for other threads of that thread block to reach that instruction, similar to how we saw for like how we saw in the case of CUDA device synchronize. So in case of CUDA device synchronize, CPU waited for all the GPU threads to finish. In this case, uh, a thread of a thread block will wait for other threads of that thread block to finish uh, before they move on to the next instruction after the sync thread. So there is a fast synchronization available for the threads of the thread block using something called a sync thread, which we'll study later in this course. Another thing is there is something called as shared memory, which is available for the threads of the thread block, which is per block. Per block, some memory is available, and these threads of this thread block can utilize that memory, uh, which is also known as shared memory. And yeah, it is very fast. I mean, it's basically the L1 cache, and accessing that memory is very fast. And this threads inside this thread block can make use of those memories, the shared memory, and can reduce the memory latency. We'll see how to use the shared memory in later lectures. Okay, so that's it. And yeah, one more thing. So multiple such thread blocks are assigned to something called a streaming multiprocessor. So in general, as we saw in the previous lecture, a streaming multiprocessor can have 1 to 5 thread blocks assigned to it at particular time. And yeah, so in general, that can be thousands of threads running on a particular streaming multiprocessor. And as we saw in the previous lecture, there are typically 50 to 100 streaming multiprocessor inside a GPU, and each streaming multiprocessor can have again 100 cores. So yeah, so and at any point in time, a streaming multiprocessor can be running with thousands of threads. And yeah, so one thing that you should note here is that a block once assigned to a streaming multiprocessor cannot go to other streaming multiprocessor. So block cannot jump from one streaming multiprocessor to other streaming multiprocessor. Yeah, so that is one thing to note about streaming multiprocessor. And yeah, then moving up in the hierarchy, multiple such streaming multiprocessor forms the GPU. And since a streaming multiprocessor can have thousands of threads running on it, in general, GPUs with multiple such streaming multiprocessor can have at particular moment tens or hundreds of thousands of threads running on it. And yeah, that finishes the GPU computation hierarchy. And yeah, so moving on to the next slide. So let's try understanding this warp in a better manner. So as I told earlier, group of 32 threads forms a warp, and all this threads, that is group of 32 threads, executes in SIMT fashion, which is single instruction multiple data. So let us try to understand this SIMT execution again with another example. let us uh, let us take this example. Let's say we have this GPU kernel, and inside the GPU kernel we have this operation vector of id equals to 0, where id is that unique id computed for each thread. And we want each memory location of that vector to be initialized to 0 using that unique id which is for each thread. And yeah, so let us see how that SIMD execution works here in this example. So whenever this warp tries to execute that instruction, what will happen is they have that single instruction, right? The instruction is single, vector of id equals to 0. So all these 32 threads are executing that single instruction, which is vector of id equals to 0. But the data items are different, right? Because thread 0 of that warp will be initializing the memory location of that vector, memory location or 0th memory location of that vector to 0, while the thread 1 of the warp will be initializing the first memory location of that warp to 0, and so on. And the 31st thread will be initializing the 31st memory location of that vector to 0. Yeah, so that is what is single instruction multiple data. So each thread of the warp are executing the single instruction, but they are working on the different data items. So single instruction multiple data. And as I told in the previous slide, warp threads are fully synchronized, that there is an implicit barrier after each and every step of each and every instruction. So as I told in the previous slide, if there is an instruction I1 and then there is an instruction I2, then it will never happen that uh, some some threads of the warp are executing the instruction I1 and other threads of that same warp are executing the instruction I2, because there is something called as barrier, implicit barrier between this each and every instruction. So once all the thread of the warp or all the 32 threads of the warp finish that instruction I1, then only they will proceed to the instruction I2. And yeah, so that's the third one. And there is something called as memory coalescence, which is closely related to this warp. And we'll see this in memory lectures, and we'll see that this warp-based execution can help in reducing the memory latencies using something called as memory coalescence. Okay, so moving on. Yeah, so the key takeaway from this slide is that there is a uh, misconception that all the GPU threads execute in lockstep manner, which is wrong. The lockstep execution is only true for the warp threads, while the across the warp, it can happen that threads are not executing in that lockstep fashion. They are working asynchronously. But within a warp, there is this lockstep execution. Across the warp, there is no lockstep execution. So please note this point. And yeah, so moving on. Okay, so as I told in the previous slide that each and every thread of a warp executes in lockstep fashion. So with this, let us try to examine this code snippet. Let us assume that this kernel, which is D kernel, named as D kernel, is launched with 32 threads, which is exactly one warp. So this D kernel is launched with 32 threads, and the way we are doing computation is as follows. We are first computing the ID, that is ID for each thread, and the ID will go from 0 to 31 since there are 32 threads. Now for each ID, we are checking if the ID is we are checking if the ID is odd. If the ID is odd, then we are executing this statement, and else if the ID is even, we are executing this statement, and then we are doing some operation. So what will happen here? So this is something interesting, right? As I told in the previous slide that all the warp threads executes in lockstep fashion. But if you see here, uh, we are launching the kernel with just one warp, which is 32 threads. But so the first statement will be executed by all the warps. But when the thread of the warps come here, they'll see that for uh, for the threads of the same warp, which are having even ID, this condition is not true. So they will have to wait or do no op here. They will do no operation because they are execute in lockstep manner, right? Because they can't just move forward, because even odd ID thread, for odd ID threads, this condition will be true, and they will be executing this statement. So even number threads will have to wait here and do no op, and opposite will be true for the else condition. Uh, Even ID threads will execute this statement, and odd ID threads will have to do no op. So, uh, so as I told, there is small addition to what I told in the previous slide. I told that all the warp threads execute in lockstep manner, and uh, they execute the same statement. As I told that all the warp thread executes the same statement, or they execute in no. So that is one addition. They will execute same statement, or they'll execute no. And when they'll execute the no, when there is something like this, when there is some condition like this, where where thread is forced to wait for other warp threads. So this is something which should be noted. And yeah, pictorially, this is pictorial representation of what I said. Considering this statement as S0, this as S1, this as S2, and this as S3, and considering that warp is just of size 8, uh, in, I mean, actually the warp is of size 32, but for this example, let us assume that warp is of size 8. Then all the 8 threads of the warp will be executing this S1. But while executing the S2 statement, odd ID threads will execute this S1 statement, but even ID threads will have to execute no op here. So S0 will be executed by all the threads, but S1 will be executed by uh, odd ID threads, and even ID threads have to execute the no op instruction. And opposite will be true for the statement S2. Even ID threads will execute the S2, and odd ID threads will execute no op. And then again S3, statement S3 will be executed by all the threads. And yeah, nop is nop is represented using this gray color symbol here. Yeah, so this is what I was trying to convey, that whenever there is a condition, it might happen that thread have to wait for other warp threads by executing the nop. So moving on. Yeah, so whenever different warp threads want to execute different instruction, they are said to they are said to have been diverged. And in order to take care of this, what hardware does, it it it's it executes the thread which are satisfying that condition. But for rest of the threads which are not satisfying that condition, it will add no instruction. uh, and yeah, yeah, it will execute the statements for, I mean, it will start executing the statements which are after that condition for the threads that satisfy the condition, and rest all will execute knobs. But there is a disadvantage to it, right? Because here the um, even ID threads are doing nothing, and here the odd ID threads are doing nothing. So ideally, there is some sequentiality which is added due to this divergence, right? Because if we were not having this condition or conditional execution, then this warp threads might have finished this statement in just a single step. But here we need two steps to execute this statement as S1 and S2, because there is the divergence among the warp threads. So there is some amount of sequentiality involved due to this divergence problem, and this problem is also, I mean, known as the thread divergence problem on the GPU. Okay, so moving on, I have a small code snippet here, and inside this code snippet, let us assume again that this kernel is launched, this D kernel is launched with 32 threads, and yeah, and inside this kernel, yeah, so it's launched with 32 threads, which is one, and inside this kernel we are again calculating the ID, and then we are having the loop here, which goes from 0 to ID, and we are doing then some computation inside that loop. So the question is, will this code diverge? So answer is yes, this code will diverge, because the reason is uh, the size of the loop is dependent upon the ID, and ID is variable for each thread, right? The thread 0 can have ID 0, thread 1 will have ID 1, and last thread will have ID 31. So depending upon the ID of thread, or yeah, depending upon the ID of thread, each thread might do the variable amount of work. And since warp thread executes in lockstep manner, each thread, I mean, the last, I mean, all the threads will at least, I mean, should wait for the last thread, which will execute the this loop from 0 to 30. Yeah, from 0 to 30, 0 to 30. So the last thread will do 31 iterations, and all the rest of the threads will have to wait for that last that for that last thread to finish, and hence this code will diverge, because there is uneven amount of computation that is happening across the warp threads, and the all the threads inside the warp has to wait for the uh, thread with longest amount, I mean, the longest amount of computation, which is the last thread. So yeah, so this code will diverge. And moving on, so again we have one more code snippet. Again, let us assume that the kernel is launched with 32 threads, which is 1 and yeah, the ID calculation is very similar as we saw. And then we have this condition as we saw in previous slide, that ID mod 2. If ID mod 2, then we execute this instruction. If else if the vector of ID mod 2 is if vector of ID mod 2 is 1, then we execute this instruction, and else we execute this instruction, and the vector is initialized as this. Okay, so we want to we want to check if this code diverges further. So let us see if this code diverges further compared to the code that we saw here. Compared to this code, does this code diverge, I mean, as compared to this code, uh, does this code diverges further, is what we want to check. Does this code diverges further compared to that code? So the answer to this is no. Why no? Let us try to understand it. So whenever the ID is odd, uh, this condition will get satisfied, right? When the ID is 1, 3, 5, then this condition will be true. Hence, odd ID threads will be executing this statement. Now, when the ID is even, what will be the vector of ID? So when the ID is even, 0 to 4, the vector of ID will be again 0 to 4. So when we do even number mod 2, the value will be 0. So when the ID is even, this condition will always be false. This will always be false. So this else if will never be. So this else if condition will be never be satisfying. I mean, will never get satisfied for any threads, and hence all these even number threads will always execute this statement. So this code is as good as writing the code that we saw in the previous slide, right? So this code is as good as saying that there is no condition, there is nothing in this line, and which is similar to the code that we saw in the previous slide. So this code will not diverge further. The amount of divergence is same as the amount of divergence in the code that we saw in previous slide. Okay, so moving on. So we say that yeah, so there is we say that there is this divergence problem, and we might feel saying that this divergence issue is because of this conditions that we had, if else conditions that we had. So is it correct to say that conditions are available in the kernel code because they causes the thread divergence? The answer is no, because let us try to understand this with the example. Let's say the value of n is 32, and yeah, so let us say that the value of n is 32, and let us say that this is id. So if that is the case, then for all the walk threads from 0 to 31, this if condition will always be true, right? Because you may take any id from 0 to 31, it will be less than 32, which is n, and hence each and every thread of the work will be executing s1. So there is no divergence, because each and every thread of the work is executing the same statement. The execution is not distributed across if else for the same work threads. Hence, there is no divergence, because every thread of the work will be executing s1. Hence, the conditions are not available. Then, okay, then we might feel saying that conditions evaluating to different truth values are available. I mean, if condition evaluates to different truth value, then there might be thread divergence. But again, this is not true. Let us try to understand with this example. Let us say that we launched the kernel with 64 threads this time, and let us see if there is divergence. So for this thread 0, for the thread 0 to 31, this if condition will be false, and for threads from 32 to 63, this if condition will be true. So 0 to 31 will be executing s2, because this if condition will be false for 0 to 31 threads, and from 32 to 63 threads they will be executing s2. So here this if condition, I mean the conditions are the condition evaluation is different for each thread, right? For 0 thread this if condition is false, but for 32 thread this if condition is true. So condition evaluating to different truth values are not able, because even they are evaluating to different truth values here, all the warp threads, that is from 0 to 31, are executing s2, and all the second warp, I mean warp threads from 32 to 63 are executing s1. So it's even false to say that conditions evaluating to different truth values are available, because as we saw in this example, even condition evaluating to different truth values for the threads uh, may not lead to the thread divergence. Hence, the takeaway is that conditions are not bad. Even the evaluating to different truth values is not bad. The bad thing is conditions evaluating to different truth values for the work threads is bad. So if within a work thread, I mean among two threads which are within the work, if the condition evaluates to different truth value, then it will cause a thread divergence. So we should make a note of this point, and moving forward. So a small classwork here. We want to rewrite this code fragment in such a way that there is no thread divergence inside this code. So first of all, this is the code snippet that we want to examine, and uh, please note that x can have this assert statement says that x can have a value of y, or x can have the value of z. So x can either be equal to y or can be equal to z, and So yeah, so the x cannot have any other value than y or z, and then we are checking that if x equals to y, then we'll assign the value of z to x. Else if x is not equal to y, which is the value of x is equal to z, which is the second case, then we'll assign the value of y to x. So yeah, this code may lead to divergence, right? Right? Because let's say the threads within the warp, for the threads within the warp, if this if condition is evaluated differently for the same warp threads, then few warp threads will be executing this statement and few other warp threads will be executing this statement. Hence, there is possibility of divergence in this code. But can we rewrite this if condition, if else condition, in such a way that there is no divergence? For that, we need to use a small trick here. And this is how we'll remove the divergence, but by replacing this if else by this single statement. So yeah, so the single statement doesn't involve any condition, and all the warp threads will execute this statement in just one go. So there is no divergence here, but let us check if the correctness is maintained. So to analyze that, let's understand case by case what is happening here. So let us say that value of x was equal to y. That was the first case, right? The value of x is equals to 1. Then in that case, what will be assigned to x here? If x equals to y, then x and x will be cancelled, and the value that x will get will be equal to z. So this is as good as writing x equals to z when x equals to y, and that is exactly what we want. If x equals to y, then x will be assigned the value of z, because y and x will be cancelled. Now let us examine the second case when x was equal to z. That's the second case, right? When x was equals to z. When x is equals to z, what will happen is now this z and this x are equal. So this z and x will get cancelled out, and this statement will turn out to be an assignment statement where we are assigning y to the x. So again, when x equals to z, this statement will turn out to be assignment of y to z, which is exactly what we want, right? So, so the cool thing here to observe is that we have removed the if-else condition and we have just turned it into a single statement. And since there are no conditions here, there is no thread divergence here. So one point to note here is that sometimes we might be able to rewrite this code with conditions in such a way that there is no condition. I mean, in such a way that there is no condition involved. And in that case, we can get rid of the divergence. But this might not be possible in every case. So yeah, but wherever it is possible, we should do it, because thread divergence can cause the sequentiality, can cause sequential execution on GPU, and hence it should be avoided. Okay, so with this, I'll end this lecture, and yeah, see you in the next lecture. Bye.